Hello everyone, welcome back. My name is Lata from Sri Venkateswara College of Engineering, the Department of CSE Data Science. Today's topic is distribution model in NoSQL. Let us move on to the topic. Distribution model for NoSQL databases. NoSQL databases, known for their flexibility and scalability, often requires sophisticated distribution models to handle a massive amount of data and user traffic. These models, unlike traditional relational databases, distribute data across multiple nodes, enabling horizontal scaling and high availability. Let us see the types of distribution model in next slide. First is single server architecture. The properties of this single server architecture is its simplicity, limited scalability, and single point of failure. Simplicity. This architecture offers a straightforward setup requiring a single server to handle all data operations. It's ideal for smaller application with limited data volumes and user loads. Limited scalability. As data and traffic grow, a single server can become a bottleneck, impacting performance and availability. This model struggles to handle high concurrency and large data sets efficiently. Single point of failure. A single server failure can lead to complete system downtime, making this model to outages and disruption. The next one is shredding, dividing data across nodes. It contains horizontal scalability, parallel processing, and improved availability. Let us see one by one. Horizontal scalability. Shredding enables distributing data across multiple servers, allowing for horizontal scaling and handling increased data volume and user requests. Parallel processing. By distributing data, operation can be performed in parallel across multiple nodes, improving query performance and reducing latency. Improved availability. Shredding enhances fault tolerance by allowing the system to continue functioning even if some nodes are down. Data is not stored on single server, so individual server failure have a limited impact. The next is master slave implication. It involves centralized control, single point of failure, scalability limitations. These are the properties of this master slave implication. Uh, in centralized control, a server manages all data modifications and writes, while slave server replicate the data for read operations. This approach ensure data consistency and avoid conflicts. Single point failure. The master server can become a bottleneck, and its failure can significantly impact performance and availability. The system relies heavily on the master server's functionalities. Now, the next point is scalability limitations. The master server can become a bottleneck as the data grows, limiting the system's ability to scale horizontally. Replication to multiple slaves can be computationally expensive. The next architecture is combined shredding and replication. It in this distributed data is there and data replication and high availability. Distributed data. The data divided into smaller chunks and distributed across multiple servers. This approach enhances the horizontal scalability and improves query performance. Data replication. The master server manages the primary data and replicas are maintained on slave servers, ensuring data consistency and availability even if one server fails. High availability. This approach provides high availability by replicating data across multiple servers, enabling the system to continue functioning even if a server becomes unavailable. The next model is peer-to-peer replication. Uh, Decentralized control, and second one is improved scalabilities, enhanced fault tolerance, potential for data inconsistencies. These are the properties of peer-to-peer replication. Let us see one by one. Decentralized control. All server in peer-to-peer replication system are equal. They can read and write data directly to their local storage, reducing the reliance on single master server. Improved scalability. A peer-to-peer replication enhances scalability by distributing the data and workload across multiple servers, allowing the system to handle increasing demands efficiently. Enhanced fault tolerance. Each server can replicate data to other peers, increasing fault tolerance. If one server fails, other peer can still access the data, ensuring continuous operation. Since there is no centralized control, ensuring the data consistency across all peer can be challenging. So, conflicting updates may occur if different peer updates the same data concurrently. This requires careful design and implementation of conflict resolution mechanisms. Consistency versus availability trade-off. Strong consistency, eventual consistency, casual consistency. Let us look into one by one. Strong consistency. All nodes see the same up to data at all times. The approach ensures data integrity but can impact availability as updates need to be synchronized across all nodes. Eventual consistency. Data is eventually synchronized across all nodes, allowing for faster updates and higher availability. This approach can lead to temporary inconsistency as data might not be fully synchronized immediately. Casual consistency, or a middle ground between strong and eventual consistency. It ensures that the writes are propagated to other nodes within a reasonable time frame, balancing consistency and availability. Scaling with distribution. First, shredding, dividing data into smaller chunks, that is shreds, and distributing them across multiple servers. These improves performance and scalability. Replication. Creating copies of data on multiple servers, ensuring availability and fault tolerance. It can be used in conjunction with the shredding. Load balancing, distributing incoming traffic across multiple servers to prevent overloading any single server. This improves performance and availability. Next, fault tolerance and reliability. Data replication, creating copies of data on multiple servers, ensuring that data is available even if one server fails. This redundancy improves fault tolerance. Node failure detection. NoSQL databases have mechanism to detect node failures and automatically route requests to healthy nodes. This ensures continuous operation even if some nodes become unavailable. Automated recovery. In case of a server failure, NoSQL databases can automatically recover the lost data from replicas, minimizing downtime and restoring service quickly. Data consistency mechanism. NoSQL databases implement various data consistency protocols to ensure the data remains consistent across multiple nodes despite failures. This guarantees data integrity and accuracy. And lastly, conclusion and key takeaways. NoSQL databases offer a range of distribution model that enable scalability, high availability, and fault tolerance. Choosing the right model depends on factors such as application specific requirements, data volume, user load, and consistency needs. By understanding the advantages and disadvantages of each models, developers can effectively design and implement a robust NoSQL solution for modern application. And these are this topic about distribution model and different types of distribution model. And thank you.